Hi, welcome to lecture number 38. This is on agriculture drainage, some related concepts. So in this, what we are going to do, we are going to see how the soil water which is present in the soil can experience different kind of the forces or the pressures. Though I have talked about this in the previous lectures. So, since we are going to talk about the drainage. So, the drainage in the sense you are going to remove water from the the ground surface or within the soil root zone. So, there is a definitely there is a wetting and drying phases simultaneously happening in case of drainage. So, in order to understand that process, so we need to know some fundamental things before going to the details on drainage. So, here the pressure in the soil water, right. So, the pressure is expressed as force per unit area, right. So, force per unit area where pressure is in pascals or in meter. I mean P is in meter, or if you have like rho W, that is in a unit weight of water in kg per meter cube, and g acceleration due to gravity. So, if you can combine one product of all these three will give the pressure in pascals. So, this is P is in head. So that is head of water in meters. So, 1 bar, and also it is expressed as bar, right. And then that is equal to 10 power 5 pascals, which is approximately equal to 1 atmosphere or 10 meter head of water. So, the negative pressure in the soil moisture, so also conventionally expressed by Pf value. So, the Pf is the logarithm of the head P, right. So, where head is in centimeter. So, if you see this graph for different soils, sand, silt, clay. So, the water content on x axis and tension on y axis. If you see this, so this is the Pf curve. So, the Pf values. So, the Pf value is a logarithm of this. So, log of these values. So, that is this is in centimeter water content. So, this is in head units, not in tension unit, but head units, and if you logarithm of that will give the Pf value. Okay. So, and the other thing is available water. So, because if you remember correctly, so the pressure at permanent wilting point, that is 10 power 4.2, something like 10 power 4 or 10,000 atmosphere onwards. So, the plants start wilting. So, then and the next one is the field capacity level. So, it has some range between 1.8 to 2.5 centimeter head, sorry 1.8 to 2.5 Pf or 60 to 300 between 60 centimeter 300 centimeter water height. So, that will be the field capacity. Okay. So, and then below this is all saturated soil moisture. Okay. So, then the next is so how, I mean what kind of this pressure we experience when you are going above water table and below water table. Suppose in this picture, if you see, so this is the ground surface, right. So, this is the ground surface, and assume that there is a manometer which is installed down in the soil. So, this is a tensiometer, right, and this is the water table. So, this is the water table, that means the phreatic surface, or the pressure at this point is atmosphere pressure. So, and the piezometer, when you install it in this, so the water level, you can see the water level at this point. Okay. So, water level at this point, because this is the water table, and then if you see the pressures. So, exactly at the surface of water table. So, you have atmospheric pressure. So, the differential pressure will be 0. Okay. So, at this point, and if you come down, that will be the pressure is positive. Okay. So, then above that, this is unsaturated condition, this is unsaturated, right, situation. So, that will experience a negative pressure here. Okay. So, suppose there is a plant, or there is a plant. So, definitely the plant experiences the negative pressure, the possibility of plant to experience the pressure is the negative. Okay. So, so basically, so here if you see, the pressure at water table is always atmospheric pressure, and the pressure below water table, so that is the more than atmospheric, right. So, there is a positive pressure. So, that means if you have a water body, right, if you have a water body and you want to insert a ball, right, you want to insert a ball. So, definitely because the buoyancy force, right. So, the ball is experience the opposite pressure, or so that means it is difficult to immerse, right, difficult to immerse. That means it is a positive pressure which is acting on the ball. So, that way you can visualize here, right. And then so the positive pressure which is measured with a piezometer, right. So, the positive pressure is measured with piezometer, whereas negative pressure which is experiencing here in the unsaturated soil, that will be measured with a tensiometer. So, the pressure above the water table, just above the water table, sorry. So, the pressure above the water table, so that is obviously less than atmospheric pressure, and the negative pressure definitely. So, the soil moisture tension is also called soil moisture tension or suction. This is measured with a tensiometer. Okay. And then, so the next is the pressure in the soil. If you are let us see the how many or what are the forces really experience in the water held in the soil particle. So, there are three forces, as I mentioned in the previous slides: the capillary force, adsorptive force, and osmotic forces. Suppose you have this is a soil particle, this is a soil particle, okay, and so and this is initially filled with water, right, completely filled with water, okay. So, it is completely saturated. So, in that case, so when there is a input water on top of this, that means the extra water which is on top of the soil. So, that will push the water due to gravity. So, the water which is going to pass into the soil body, and so when there is no input, what happens? So, the whatever water which is experiencing with the gravity will be percolating down, right, will be percolating down, and remaining things. So, remaining you will be having some water, it is not 100% will be depleted, but some water will be held with the soil particles, right. So, this is the water which is held with the soil particles, and so this is the air space, right. So, there is no water here. So, this is all water held to this. So, so this water is held by some forces. So, that is the capillary forces, adsorptive forces, because these two different materials like soil and then water. So, definitely you experience, the soil experience the adsorptive forces, water experience the adsorptive force. Then other one is osmotic forces. So, this is basically due to the soil salinity. So, if you have a saline salts present in the water, so that definitely does not allow water to flow out, and so that also helps in water to held with the soil particle. So, then what is the capillary forces? So, capillary forces are like, if you see this picture, the side picture. So, assume that there is a tub of water, right. So, assume that there is a the water which is present in the tub, and you put tubes of different diameters, right, with increasing diameter. So, if you observe the water levels here, so the pipe or the tube with the lower diameter has I mean the water rise high compared to the other diameters. Okay. So, that means this clearly indicates when the soil pores are in less diameter. So, that will help in raising the water through capillary forces. Okay. So, the capillary action, this is also called capillary action, also referred as the capillary motion or capillarity. So, this is a combination of cohesion and adhesion of surface tension forces. So, this is basically happening due to surface tension. If you see water which is present in the glass of a tube, right, it has some bending, the curvature at this one. This is basically due to surface tension forces. Okay. So, but basically this is happening with the cohesion or adhesion. So, the cohesion forces are like the forces between the similar molecules like water molecules within the water, or adhesion, this is opposite, different molecules like here the glass and water. So, that is there is a force of attraction between that, and surface tension. So, that is due to the pressure or acting on top, and then the water pressure here. Okay. So, then and the capillary action is demonstrated by the upward movement of water through a narrow tube against the force of gravity. So, this is an example of how these capillary forces act on different diameter of pipes or different diameter of glasses. Okay. So, that means the lower the diameter, the rise of capillary rise will be high. Okay. And then if you see this still the capillary action. So, when there is the adhesive intermolecular forces between liquid such as water and the solid surface of the tube are stronger than the cohesive intermolecular between the water molecules. Okay. So, when there is a adhesive forces are higher than the cohesive forces. So, then the surface tension definitely influence more, and if you see this equation, so which is used to estimate the rise, height of capillary rise, that is H c, which is equal to minus 2 gamma cos theta by rho g r, okay, where gamma is the surface tension in Newton per meter, and H c the capillary rise in meters, and r radius of curvature. If you see this, so this is the tube diameter. So, the radius of curvature. So, here if you see, so this is the curvature, right. Okay. So, this is the radius of curvature r, and then rho is the unit weight of water and z acceleration due to gravity. So, you put all these values together, then you get the H c, and then so here the theta indicates the surface, the tangent of the curvature. So, this is the tangent of the curvature theta. Okay. So, if this theta is equal to 0 as you mentioned, or less than, or theta is equal less than 90 or 0, right. So, that means so that 0 means exactly it is falling here, right. So, there is no surface tension. Okay. So, when theta is equal to 90 degree, that is the maximum, theta is equal to 90 degree. Okay. So, theta let us say 90 degree, then you get you get H c is equal to minus 2 gamma into rho g r. Okay. So, that means theta, when theta is equal to 90 degree, theta is equal to 90 degree. So, this will be 0, that means, so no rise. So, there is no surface tension, no rise. If theta equal to 0, so you get the maximum surface tension, that means H c equal to so then H c equal to minus 2 gamma cos theta by minus 2. So, that is equal to minus 2 gamma rho g r. Okay, where theta equal to 0, that means cos theta equal to 1 and minus 2 gamma rho g r. So, this is the maximum rise you can expect when theta equal to 0. So, when theta equal to 90, you get Hc equal to 0. So, that means you may expect here the same. Okay. So, that means there is no angle at all. I mean, this is a 90-degree angle. Okay, at 90 you experience no rise. Okay, so in a pore curvature of meniscus attains a maximum value when the radius of equal to the radius of pore, that is theta equal to 0. So, when radius of pore r is equal to radius of the curvature, radius of curvature r, let us say. So, r dash equal to r, then you that means your theta equal to 0. Okay. So, then you experience the maximum rise. Okay. So, here you substitute for r equal to 2d, okay. R is equal to 2r is equal to d, right. So, substituting that r is equal to d by 2, substitute r equal to d by 2, you get minus 4 gamma r g d. Okay. Or you put all the values of rho g, because rho g is 9.8, rho is equal I mean 1000 kg per meter cube, right. Substituting everything, you get Hc is equal to minus 3000 by d, where d is in microns. So, okay. So, the usefulness of this equation Hc is equal to minus 3000 divided by d, right. So, for a particular, so knowing the diameter of a pore, you can I mean predict the water rise or capillary rise in the soil media. Okay. Yeah. So, then the next is that is the capillary forces, the other one is adsorptive forces. So, this includes van der Waals, which are weak forces, and electrostatic forces exerted on the water by changing or charged colloidal surfaces of the soil particles. So, this is basically, because the colloidal particles which are in the soil have charge. So, that is electrostatic forces and also van der Waals forces. So, that all combines will help in attaching the water molecule to the soil, that is adsorptive forces. So, the tensiometer is generally used to measure the metric suction, which is capillary and adsorptive forces. So, both capillary and adsorptive forces will be measured with tensiometers. Then the osmotic pressure. So, osmotic pressure is mainly due to the salts present in the water or right in the soil water. It occurs when the solution different concentrations are separated by semi permeable. Suppose in this case, so assume that there is a semi permeable membrane between the fresh water and the salt water, right. So, then after some time there is a interaction, there is like the fresh water molecules go in and then the salt molecules go into the fresh molecule. So, after the equilibrium, so you see the rise in water level in case of salt. So, that means this is acting like a barrier, right. So, this much I mean this definitely creates an extra suction. So, right, this is a negative pressure, if you see, right. So, that is causing the suction, that means attaching the particles here. So, the random motion of the water solute molecules create a net movement of water to the component with higher concentration until equilibrium is reached. Okay. So, once it is coming to the equilibrium, you will see the fall in fresh water and rise in salt water, and that the fall definitely causes the suction. So, at an equilibrium, so the net water movement is eliminated by the increase in water pressure. So, that is so that is basically by increasing the water pressure. So, this is an example of reverse osmosis. So, right, increasing the pressure, what happened? So, in case of reverse osmosis, generally you see in the water filters, right. So, the salt water in this case of whatever the water which is the dirty water can be I mean pass through the semi permeable membrane, and then the fresh molecules will be going to the a fresh water molecule going to the fresh water, leaving the I mean salt molecules on the other side. Okay, the soil moisture characteristic curve. So, this before that the total water potential, so which is equal to the gravitational potential, metric potential and osmotic potential. So, these three potentials, so we experience. So, I mean the soil has gravitational potential because when it is saturated condition, the gravitational potential, and then once it is at field capacity and the metric potential, and of course, the osmotic potential if there is a salts. And the relationship between the soil moisture theta and metric potential psi m, this is the soil moisture characteristic curve, this is the suction, and then this is the theta. Okay. So, if you see this, so initially the water is saturated, so that is at let us say the maximum water content. Then after that, if you remove water, let us B point, it comes to this point, right. So, that means less water and corresponding pressure, right. And if you remove further water from there, see it goes here, right, and corresponding the tension. So, that means if you have this much tension, so that will remove the water and stays at this moisture content. And if you create this much suction, right, the suction will help in taking the water, and the soil is at this moisture content. So, similarly, D point, this is the dry phase, if you see. So, you have to, in order to have this much soil moisture, and you need to have this much suction to remove water. Okay. So, the soil moisture characteristic curve is the curve between theta and psi. So, psi here the source total I mean psi t we are talking about. Okay. And then so used to predict the soil water storage, I am sorry. So, here the metric suction, this is, so this is soil psi m only. So, psi g and psi o, if there is, so these we are not considering here, okay, because anyway psi g for gravitational it may not be. So, once it is in field capacity, so the only this psi m. Okay. And then due to the hysteresis, so here if you see, so this is when you remove water, so the curve goes like this. Okay. So, when you see the opposite, so start adding water slowly, right, slowly and corresponding pressure. So, it is supposed to follow the same curve, but it does not because of the hysteresis effect. So, this hysteresis is more common in case of clay soils than the sandy soils. Okay. For drainage purpose, so drying curve is more relevant, because in the drainage we remove water, right. So, we remove water from the root zone. So, that means, so the drying curve is so this is a wetting curve and this is a drying curve, right, drying curve. So, the drying curve is more relevant in case of drainage. Okay, so, this is the soil moisture characteristic curve, the same thing, the soil water content in percentages and soil moisture metric potential, that is in bars. So, for different soils, so look at this is the sand, this is the sand, this is the loamy soil, and this is a silt soil, and I am sorry. So, this is the clay soils. Okay, sorry. So, this is so this is the sand and this is the clay. So, the colors are like that. So, the capillary rise I was talking. So, H c which is equal to minus 4 gamma rho z d or minus 3000 by d. Suppose at minus 100 centimeter H c is equal to minus 100 centimeter. So, the pore diameter with 30 microns will completely drain. Okay. So, at minus 10 centimeter, see the pore diameter at 300 micron pores will completely drain. So, at 10,000 centimeter rise in the sense, so at moisture, so 0.3 micron diameter pores will completely drain. So, this formula is very important in order to understand. So, what is the suction or what suction the corresponding soil particles having the diameter is going to release that water. Okay. Yeah, so soil water potential here. So, this is a potential diagram. So, in order to understand soil water potential, so this is the land surface, okay, and let us say this is the water table. So, let us assume a point A in unsaturated, this is unsaturated, right, and this is saturated. So, let us assume a point in unsaturated stratum, that is point A. Similarly, in saturated point B, right. So, then definitely we experience negative pressure here, and here we experience positive pressure P B. So, taking the water table as reference, okay. So, and this Z A, so definitely you have to do positive work in order to take or lift water from this point to this point, right. So, that is why Z A is positive, whereas P A, that is a metric potential, that is a negative. So, at this point what happens? So, since the water table on top, right. So, you need to do a negative, of course, the pressure is positive here, right, it is more than atmospheric pressure, but the elevation head which will be negative, because when you put like as I mentioned, when you put the a ball inside, right. So, it is very hard to push it to this level, because there is an opposite pressure acting on top. So, that is why, so Z B is negative here, Z B is negative. So, putting everything together here in the, this is called the potential diagram, okay. So, so this is a site, this is an equilibrium. So, once the soil moisture which is present in the water in the soil is in equilibrium, so psi t at any point will be, this is total water potential will be 0. So, and then this is water table level, right. So, so since here from here, so Z A is positive. So, Z A, this is the positive side, whereas P A is negative. So, P A is the negative side, right, P A negative side, and then the other side. So, the P B is positive side. So, this is positive, and Z A is negative side, this is a negative side. Okay. So, the advantage of this is at any distance, right, this is if this is the distance, right. So, you will be able to find out what is the P B and corresponding what is the Z B, okay, Z B point and P B point at a particular distance. Okay. And then, so at this point, exactly at this point, this is another equilibrium. So, psi t is equal to 0, that means, so Z A is positive, right. So, at this point Z A is equal to P A. So, similarly here Z B is equal to P B at this point. So, this is definitely the field capacity situation. And field capacity situation, so once the loose water came out, so that means under equilibrium condition, exactly at the equilibrium condition. So, the total T which will be 0 metric potential at that point. Okay, so, then next is as we know this total T is psi g plus psi m. So, energy needed to move against gravity, psi m is energy needed to move against pressure. So, at point A, if you recall the previous picture, so Z A plus exactly at point A. So, psi A is equal to Z A plus minus P A, and at point B psi B is equal to minus P into minus P plus P B. P B is positive here because this is below the water table, P B is negative here above the water table. Okay. Under field capacity situation, no evaporation, the water will be percolated until P A is equal to Z A. Okay. So, that is under field capacity situation. So, the P A is equal to Z A. So, at point A, the total capacity potential is equal to gravitational and metric. So, the gravitational is Z A plus metric potential is again minus Z A, because Z A is equal to P A, right. So, minus because Z A plus Z A minus P A, Z A minus Z A. So, that will be 0. So, similarly, for 0 flow in the groundwater point B, so you get the same thing 0. So, that means at equilibrium point, at equilibrium the total water potential is 0. And then the Darcy's law, so it clearly states the principle that governs the fluid moves in this subsurface called Darcy's law. So, Darcy's law, so mainly what we are assuming in this case, soil is saturated, flow through soil is laminar and is continuous and steady. So, this under this assumption, so the basically this is the equation Q is equal to minus K into H out minus H in by L into A. So, where if you have a specimen of saturated soil media which has area of cross section A, and so this is the inlet and outlet, you are collecting Q amount of water. So, this is the datum. From the datum you observed there is a water level at the inlet is H in. So, water level at the outlet is H out. So, the difference will be the pressure gradient. So, that pressure gradient is really helping in moving the fluid from point 1 to point 2. Okay. So, the Q which is collected here, so that is the of course, this is capital Q. The Q is equal to minus K into H out minus H in. So, it is a difference in pressure divided by L. L is the length of the specimen. So, or the finally minus K into delta H by delta H by L by A into A, then Q is equal to K I A. Okay. So, the basically, so the K or the Q is directly proportional to the K. Okay. So, Q is equal to K when the hydraulic gradient is unity. Okay. So, that A is equal to when A is equal to 1 and d H by L which is equal to 1. In the two cases, the Q which is nothing but hydraulic conductivity. Okay. So, it basically depends on of course, the geometry and the distribution of water filled pores. Okay. So, the hydraulic conductivity as I mentioned previous slide, it is the velocity to applied hydraulic hydraulic gradient. So, for unit hydraulic gradient, right, and which is having unit cross sectional area. So, the flow through the saturated media is equal to the hydraulic conductivity. So, if you see the K sat meter per days, the coarse sands 10 to 15 and dense clay which is less than 0.002, that means definitely influencing the soil texture, right. So, and also the pore space. So, increasing pores, it is easier to pass, and you had I mean higher hydraulic conductivity than the pore space which is smaller. So, that is difficult to water to flow in to the soils with lower pores, for example, the clays. And in this case, in case of drainage point of view, the temperature effect is negligible, and value are low when the water has follows the tortuous through the soil. Suppose you have a definite pores versus you have the small pores, right. So, the water will pass through one like this, as well as a direct path. So, the flow path in case of smaller pores is a long path. So, that means the tortuosity is higher. So, that means in this case the hydraulic conductivity is lower than the other case. So, here it is a free flow. Okay. So, how to measure this saturated hydraulic conductivity? So, the simple method is the constant head per millimeter method. So, from the field you collect the core sample, right. So, the core sample is this is the sample, right. So, this will be attached to the two filters, the filter 1, filter 2, then this is a storage reservoir, the outlet reservoir. So, the water will be flowing continuously or the water will be flowing continuously from the bottom, right, from the bottom, and then so the difference in water levels, right, difference in water levels will be delta H. So, that will be knowing, and the sample area of cross section, right, length, okay, and then the outflow here the Q. So, that is the Q. So, then finally, you get K s. So, the other way is saturated hydraulic conductivity is the inverse auger hole. So, in the field you make a hole, that straight hole which has a diameter 2 r, right, and so this is initial put the water. So, let it saturate completely, the media is completely saturated, then after some time start the experiment. So, initially you fill the hole with some water level y 1, and then after some time see the note down the next depth y 2. So, that is delta y. So, the K s is estimated with 1.15 r, which is the diameter of radius of the hole, tan alpha, where tan alpha is equal to y 1 0.5 r minus log y 2 0.5 r divided by t minus t 0, t 0 initial time and the final time. So, putting all the values you get K s value. And there is a this is another method, is the ring infiltrometer method. So, in ring infiltrometer what we do, so at particular time you find out the velocity, the infiltration rate. So, that goes like this. So, the last one which is constant, that is called basic infiltration rate. So, generally we take it as K s. Okay. So, K s is equal to F naught. So, this is another method. So, this ring infiltration meter data, and finally, the last points. So, with time if you see, so that is K s here 10 mm per hour. Okay. So, this is F is centimeter per hour, and this is time. So, if you see the graph is going to fall and the last point. So, that almost the infiltration rate is constant. So, that is equal to the K s. So, there is a software also available, it is called Rosetta. So, it is available at ars.usda, and then in this software, so basically it requires soil texture information. So, like percentage of silt, sand, silt, clay and bulk density. So, knowing these values, right. So, and then you can predict the Van Ginsten parameters, and then finally, the K s also, right. K s also you can estimate using the soil information. So, this is pretty easy and straightforward. So, pedo transfer functions or pedo that is a soil. So, transfer functions means knowing the soil information like percentage of silt, sand, clay, organic carbon. So, you can derive other soil hydraulic parameters or soil physical properties, soil hydraulic parameters like K s, theta s, theta r. So, there are even soil moisture characteristic curve, right. All things can be estimated or calculated using this. Okay, so this is all in this lecture. Thank you so much.